Okay, welcome back, and today we are going to finish up Chapter 4, and this section we're talking about applications of models of exponential growth and decay. So these are going to be application models that use basically everything that we've been talking about in this chapter. Okay, so here's where it all gets applied to real-life examples. Okay, so again, in many situations that occur in ecology, biology, economics, and the social sciences, the quantity changes at a rate proportional to the amount that's already present. In these cases, the amount present at time t is a special function called the exponential growth or decay function. Okay, so we're going to let y naught, y sub 0, be the amount or number present at time t equals 0. And then under certain conditions, the amount present at any time t would be modeled by this exponential growth problem, okay, where k is some constant. Okay, so this is the initial amount, and then this is our exponential growth, our factor by which it's growing by over time, and that's going to give us the present value, or the value at some time t. Now the constant determines the type of the function, okay, whether it's going to be a growth function or a decay function. So if k is positive, we're going to have an exponential growth function. If it's negative, it's going to be a decay function, for example, in radioactive decay type situations. So in this, earlier we had this example, okay, and now let's use this table to determine such a function of the data. Okay, so this was the year and this was the carbon dioxide. So to find an exponential function that gives the amount of carbon dioxide y in years, dioxide y in years or x, so the data points showed that there was an exponential growth. So the equation will take the form of this. Now we must find the values of y0 and k. Now the data began with the year 1990. So to simplify our work, let 1990 correspond to x equals 0. Okay, so in 1991 will correspond to x equals 1 and so on. So since y0 is the initial amount, 353, in 1990, then we can plug in 353 here. Okay, and so now we get this. Okay, so now we still need to figure out k. Okay, from the last pair of values in the table, we know that in 2275, the carbon dioxide level is expected to be 2,000 parts per million. And then in the year 2275 corresponds to 285. So what we're going to do is we're going to substitute in 2,000 for y and 285 for x. And then we're going to solve for k. Okay, so we're just using one of the points, the last point, to figure out a value for k. And so we divide by 353. Then we're going to take the exponential of both sides, natural log of both sides in this case. And so we're going to get 285k is equal to the natural log of this quotient, and then we're going to divide by 285. And so we get k is approximately equal to 0.00609. And so now we've got our function. Okay, so this function models the data given. Okay, now we're going to use this model to estimate the year when the future levels of carbon dioxide will be double the pre-industrial level of 280 parts per million. Okay, so which would be 560. Okay. Okay, so when is this going to be double? Okay, well we're going to use 560 and then solve for x. Now we're going to basically go through the same process. Divide by this and then take the natural log of both sides. Okay, and then this is going to come down and this is going to become 1. Okay, and then we're going to divide by our coefficient here. And then we get x is equal to this, or approximately 75.8 years. And since 0 corresponds to 1990, we're going to add 75.8 years. Okay, so we're going to be in the 75th year after 1990, which puts us during 2065. So that's when we'll hit double. Now, how long will it take for the money in an account that accrues interest at a rate of 3% compounded continuously to double? Well, let's figure this out. So this is the compounding question. Well, we know that the formula is going to be the future value is equal to P, the initial deposit, and then times E to the RT. This is for continuous compounding. Okay. And we want to know, hey, when is it going to double? So that means our future value will be double this value, so 2 times P. And if we divide by P, well, it just becomes 2. Okay. And then if we take the natural log of both sides, then this is going to become 1, and we get this out. And now we just divide both sides by 0.03, and we get T is approximately 23.1 years. Okay, so approximately 23 years for your money to double. Here's another one. So it says, according to the U.S. Census Bureau, the world population reached 6 billion people during 1999. Okay, and it was growing exponentially. By the end of 2010, the population had grown to 6.947 billion. The projected world population of billions in T years after 2010 is given by this formula. Okay? Now, based on this model, what will the world population be in 2025? Well, since T equals 0 represents 2010, so we're going to say T is the years after 2010. In 2025, that would be 10 years that passed. Hold on a second. Yeah, that's 15. This is a typo. This is 15. So T is equal to 15. That's a typo. Obviously, it's not 10. And so what we're going to do is we're going to plug in 10 and solve directly. Right? So we can just stick this into our calculator and find that it's going to be 7.768 billion people in the world by 2025, according to this model. Okay, now what about, it says, in what year will the world population reach 9 billion? So now we're going to set this equal to 9 billion because that's what we want to solve for. And now we're going to divide by this and then solve this. So we're going to divide by the coefficient here. Then we're going to take the natural log of both sides and then divide by this. Okay, so we divide by this, take the natural log of both sides. Okay. And then we're going to get this. This is going to come out. Then we're going to divide both sides by the coefficient here to get this. Stick this in our calculator, and we get 34.8 years. And so what does that mean? It means that, well, 34.8 years after 2010, which is going to be what year? 44.8. So during the year 2044, the population is projected to reach 9 billion based on this model. Okay, what about this one? Let's say we have 600 grams of a radioactive substance that are present initially, and 3 years later only 300 grams remain, so half. Determine the exponential equation that models this decay. So this is going to be a decreasing function, so k is going to be negative in this case, so let's solve for k. Okay, so we know the initial value is 600, right? So we know that this is going to be the model. We got to solve for k, so we know that half was left over after 3 years. So we're going to stick 3 in for t, and we're going to stick 300 in for y. Okay, and now we're going to just solve for k. So we're going to divide by 600 to get 0.5. Then we're going to take the natural log of both sides. Okay, and then we're going to get 3k equals 0.5, or the natural log of 0.5, I should say, and then divide by 3. And then k is approximately equal to negative 0.231. Okay, and so now we've got the constant. We can plug it back into our equation. So this is going to be the model that represents this decay. So now, how much of the substance will be present after 6 years? Okay, now we've got the function, so now all we have to do is represent, let t equal 6 years, and we're going to plug in 6, and we find that y is 150, so we'll have 150 grams approximately after 6 years. Okay, so that makes sense because after 3 years, right, we had half, and then after another 3 years, we have half of that. Now, carbon-14 is known as a radiocarbon. It's also a radioactive form of carbon and is found in all living plants and animals. So after the plant dies, obviously it stops producing this isotope of carbon-14, and this is radioactive, so it starts to decay. And so we can use the amount of carbon-14 that remains in the dead plant or animal and compare it with the amount of radiocarbon that is present in living things today and find out how old it is. And this is called carbon dating or radiocarbon dating. Okay. The amount of the radiocarbon present after 2 years is given by this equation. Okay, so the half-life, incidentally, is about 5730, so about 5,730 years if you were to find the half-life. Okay, but this is the formula that's used. Okay, so here it says find the half-life of carbon-14. Ooh, let's see how accurate I am. So half-life means I'm going to have 1/2 of the initial amount left over. So again, I'm going to replace y with this, and then we're going to solve for t. Okay, so this is our initial value. The half-life means I'm going to have half of this, so this is going to be 1/2 y0, and then I'm going to divide both sides by y0, and I'm going to get a half again. And then I'm going to take the natural log of both sides, right? And then I'm going to divide by this. And plug it in your calculator, and you get approximately 5,700 years. Okay, all right. So the half-life is 5,700 years, or approximately. Okay, what about this one? Charcoal, which is carbon. From an ancient fire pit on Java, contained 1/4 of the carbon-14 of a living sample of the same size. Estimate the age of the charcoal. Okay, well here we know that the amount of carbon was 1/4 of the initial amount. So we're going to plug in 1/4 y0 here and solve. So we just take the natural log of both sides, and then we're going to divide by the constant, and we get T, and then T is approximately 11,400 years old is the rock, or charcoal. Okay, what about cooling law? Newton's law of cooling. Okay, so we're going to have something that's either that's hot, right? Certain temperature of an object based on its surrounding temperature. And so if we want to find how fast, or we want to find how it cools, then we can use this equation, this function. So the temperature of an object is dependent on the outside temperature, or the surrounding temperature. This is the temperature of the object. This is the exponential function here that models the cooling of the object. Okay, if it starts at this temperature. Okay, notice it's negative K. K is assumed to be positive here. Okay, and C is the initial. What is C? Oh, C is a constant. Okay, C is a constant. Okay, so let's use this function to answer some questions. So it says write an equation that models the data. So it says a pot of coffee that's at 100 degrees Celsius is set down in a room that's 20 degrees Celsius. Okay, the coffee cools to 60 degrees after 1 hour. Okay, so let's use this information to write an equation that models the data. Okay, so we're going to have to find the values of C and K in the given formula, and then that'll tell us what the model is going to look like. So when T equals 0, the initial temperature was 20. Right? So this is 20, so this is the temperature of the room. That's not going to change. And the temperature of the coffee at f of, which is f of 0, is 100. Right? So that was the initial temperature, f of 0. Okay? Also, when T is equal to 1, it's 60. So we're going to substitute the first pair of values into the function along with T naught equal to 20. Okay, so here's our formula. We're going to stick in 20. Okay, so the initial temperature of the room is 20. Okay, the function here is 100, so the initial temperature at T0 is 20. Right, T is 0. So this is just going to be 0, which means this is going to be 1. So we're just going to get C plus 20 equals 100. And so C equals 80. So we found the first one. Okay. Now we just got to figure out what K is. Okay. So now we found that, hey, after 1 hour, the temperature of the pot was at 60 degrees. So now we can plug in 1 and 60. Okay, now we can solve for K. So we simplify this. We get 40 equals 80 times e to the negative k. And we get 1/2 is equal to e to the k, and we take the natural log of both sides. And we get negative k is equal to the natural log of 1/2, or k is equal to the negative natural log of 1/2, which is approximately equal to 0.693. And so now we've got our model. So this is the model that's going to model the temperature of the pot over time t, which is in hours. Find the temperature after half an hour. Okay. So half an hour, so t equals 1/2. And so we're going to just plug in 1/2 here, and then just solve. So let's just solve. And we get half an hour later, the temperature should be 76.6 degrees Celsius. Okay, don't forget your units. How long will it take the coffee to cool to 50 degrees Celsius? Okay, well, we want to set f of t equal to 50 now and solve for t. So now we set this equal to 50. We want to solve for t. So again, we're going to subtract 20, then divide by 80. And then we're going to take the natural log of both sides. And then we're going to divide by this number here. And t is approximately 1.415 hours. Okay, so approximately an hour and 25 minutes. Okay, and that is the end of this section and the end of the chapter. And that's the end of all new material for this class. And again, please make sure you're practicing. Go back to these examples, do the other examples or exercises at the end of the section in the textbook. If you get stuck on homework problems or any of those types of problems, exercises, examples, please email me or let me know in class and we can work those out and together in class and figure out the answers to your questions. Until then, keep practicing and I'll see you later.